Ladies and gentlemen, welcome to San Antonio. Please take your seat. Silence your phones. We are about to begin.
"50 years. A lot has happened in the last half-century. The world has changed, people have changed, the profession has changed. We have grown from US-based to international, from paper to paperless, from impossible to everyday. And right in the center of it all, that is where you will find us, the Society of Research Administrators International. It all started with a single vision in 1966, to create a community. For 50 years, SRAI has been preparing research administrators for the ordinary and extraordinary in order to make the most of their professional development. We began in 1966 with 4 people, and today we are an association with over 5,600 members on 6 continents.
I've been a member of SRA since 1978.
I joined in 1971, and in those days, research administration was a very new profession. And it was the one group where I could meet and find peers that shared the kind of background and issues and experiences that I had.
Members are important for SRAI because they are the association. The members inspire and develop this community. It's a place to feel welcomed, to be heard, and to be part of something special and meaningful. SRAI is built on the cornerstone of its diverse and open membership. The primary function of SRAI is to provide training to research administration professionals, whether attending a conference, participating in a committee meeting, or socializing at a networking event. Members can connect with other people, learn about the industry, and build relationships.
All these connections that I've been able to make has helped me understand the way in which research administration is done. There are connections that were only possible in part by attending SRA meetings that we've had over the last decade or so.
Just the amount of experience in one place makes SRA very valuable to research administrators.
The reason I come here is because of the quality of content, the range of people that I can meet, and the benefits it gives to me for professional development.
I have been a member of SRA for about 4 or 5 years. I enjoyed, meeting new people, the activities that incorporated both the research administration and the social connections. Now I know many people from across the USA that I can relate to.
Over the last 50 years, we have given research administrators more ways to develop professionally, personally, and socially through a strong community. SRA International drives progress. SRA International provides balance in your career. SRA International connects you.
The value of SRA is in many dimensions. I've gotten so much value out of being involved with the people in SRA, both the volunteers, primarily the volunteers, and the people that are involved in the SRA corporate offices. Those connections that I've made with people all across the country and internationally have meant the world to me. They've bolstered my career. They've given me expertise in areas that I didn't have expertise.
The profession of research administration and management is growing, but there are still many more opportunities out there yet to be explored, to share new ideas, to conquer the new global challenges together.
My first involvement with SRA was in the Milwaukee meeting in 2005. We wanted to publish and present some very innovative work we thought we'd been doing. And we thought there was no bigger venue than SRA.
These 7 or so years that I've been consistently participating in SRA activities since 2009, I really got quite a bit of a head start on the type of things that we need to put in place to have a functional research and technology transfer office.
I'm very pleased because SRA is an association that values these people and the professional development. So we are very glad to be here.
So as we look toward the future, we remember how and where we started. As a simple idea of bringing research administrators together as a community. Together, we make the profession smarter, stronger, and more global. Be part of the progress. Your voice matters in this community. Be part of SRA International.
Good morning, guys. Good to see you made it back from the ranch last night. It's a pretty impressive show, I'd say, with those longhorns. So I'd like to welcome all of you, and we want to kick off our 50th anniversary. This year marks the celebration of our 50th anniversary. It was SRA was founded in 1966 and incorporated in 1967. And while times have changed since 1966, our foundation of dedicated members has remained the same. I stand here with just a few of our past presidents that have, along with many past officers, volunteers and contributors, shaped the SRA into what you see today. So I want to introduce 9 of our presidents. As Sandra Nordahl, 2012 to 2014. Oh, you're all there. Jim Hanlon, 2010 to 2012. Pam Miller, 2008 to 2010. And Spanky McAllister, 2004 to 2005. Michael Owen, 2003 to 2004. Elliot Kulakowski, 2000 to 2001. And we have the infamous Bill Swery, 1997 to 1998. We have Ruth Poole, 1993 to 1994. And this is really impressive, Linda Halstead, 1983 to 1984. So thank you, guys. Thank you for being here. It's back to pasture now. Before we get started with the program and the keynote speaker, I want to talk about the last year's milestones. You will see posters that celebrate our 50 years of collaboration, knowledge, and excellence. Looking back on this year, those words hold true like never before. SRA has always been an association of members for members. We actually reached a record high of 5,600 members this year, which is really impressive. We continually strive to create new opportunities for members to collaborate and engage. So for instance, the membership committee has expanded our ambassador program to a year-long activity, so to provide activities or opportunities for members to stay connected even after they leave the conference. The SRA Journal, which will go open source this fall, has created a fellowship program for aspiring new authors. This is really great. And our monthly catalyst continues to add new feature articles and contributors. Over this last year, over 5,000 individuals have participated in our educational programs. And that's everything from section meetings in New York City to Portland, to online webinars, to chapter meetings. So SRA International is committed to fostering a positive and enjoyable educational experience, which is flexible, targeted, and engaging for advancing all levels of a research manager's professional career. We've held training programs in uniform guidance, basics of research administration, grants and contracting, research integrity, departmental administration, and much, much more. So I'll thank all our speakers and volunteers to make all this a success. I would like to recognize a few people. And when I mention those people, please stand up so you'll see how many people are actually engaged. So the board of directors, please stand up. Nobody wants to stand up? Okay, we have section, chapter, and division officers. Good. We have committee chairs, so not everybody's sleeping in. And all those of you who have been officers in the society, please stand up at some point. Very good. Apart from all our dedicated members, we also have some invited guests from fellow organizations. I would like to recognize them. We have Robert Andresen, who's the president of Incura. I know he's over there. We have Carrie Thomas, who's down here from the Association of Independent Research Institutes. We have Antonio Flores, the Hispanic Association of Colleges and Universities. We have Dr. Francis Chandler from CARA. We have Professor Eli Wakishaya from the Eastern African Society. We have Lindsay Dixon from ARMA in the UK. We have Cynthia Hope from the FDP. And apart from those guests, I really want also to recognize our corporate partners and thank for their really, really good cooperation with us. So we have eVisions, Picori, InfoEd, and iMedris. So thank you guys for working with us. And ladies and gentlemen, now I'd like to introduce the 2016 annual meeting co-chairs, Ed Black, Kathy Brownridge, and Andrea Deaton.
Thank you all for coming out so early this morning. Wanted to mention a few things this morning as we get started. First and foremost, hope you all have some time to explore the River Walk. If you don't know what that is, either talk to one of us. It's just basically right outside our doors here. It's a nice, beautiful walk of the river, but there's shops, there's things to see along the way. It's a great thing to check out. So we are anticipating 1,500, so 1,500 attendees to this meeting from over 25 countries. So this is truly an international group. We have 240 speakers, 135 sessions, 37 exhibitors, and that's packed over the next, really 2 days. I mean, we've got lots of opportunities to attend a session that you would like to see. If you happen to see something that maybe you don't like, keep looking. There's a lot of opportunities to see something that you can attend. Please explore the exhibit hall, which is just right here behind us. Check out all of the exhibitors. Also enjoy the SRA talks. This is an opportunity for you to hear a little bit more from our exhibitors of what they offer. And of course the Internet Lounge for checking email and whatnot. So on behalf of my fellow co-chairs, Andrea Deaton and Kathy Brownridge, I choked on. We want to wish you a wonderful conference, learn lots, enjoy, and network, and that's it.
Hi, folks. I've got the great pleasure of introducing now the keynote speaker to you all, who's travelled all the way from the UK, so I'm delighted she can be with us today. Professor Sheila Rowan is an experimental physicist, and since 2009 has been the director of the Institute for Gravitational Research in the School of Physics and Astronomy at the University of Glasgow in the United Kingdom. Prior to that, she held positions split between Glasgow and Stanford University in the USA. The research of her institute is focused on developments relevant to the international network of gravitational wave detectors, and in particular has been an international partner in upgrades to the US LIGO observatories carried out between 2010 and 2015. This research contributed to one of the most significant scientific breakthroughs of this century, the first detection of gravitational waves, announced in February 2016 in the 100th anniversary year of their prediction by Albert Einstein. This discovery has opened up an entirely new field in physical science that of gravitational astronomy, enabling the study of black holes and other exotic phenomena far out in our universe. Sheila's personal research is targeted at developing optical materials for use in gravitational wave detectors, along with broader applications in precision measurement science. She was awarded a Leverhulme Prize for Astronomy and Astrophysics in 2005, appointed to a fellowship of the UK Institute of Physics in 2006, elected to a fellowship of the Royal Society of Edinburgh in 2008, was the recipient of a Royal Society Wolfson Research Merit Award in 2010, and awarded a fellowship of the American Physical Society in 2012. Sheila was made an MBE for Services to Science in the Queen's Birthday Honours List in 2011. In 2014, she was selected as their annual Women in Physics lecturer by the Australian Institute of Physics. She is currently, since 2016, seconded part-time to the post of Chief Scientific Advisor to the Scottish Government. If you'd like to ask Professor Rowan a question, you can submit them online or via text or tweet, and the instructions for this are on your table. I'd now like to hand you over with greatest of pleasure to Professor Sheila Rowan.
Well, thank you very much to Kathy and to the other organisers of the meeting here for the invitation to come and talk to you. I'm absolutely delighted to be here. I know you're all having breakfast. I'm going to give a bit of a mixed talk this morning. And I was delighted to see the strapline for your meeting of explore, educate and engage. And I hope that the talk this morning will do a bit of a mix of those things. And I'll also, as I go through, try and explain how what we do as scientists in this new field also tries to address those three areas. So we're going to do a bit of science this morning. And so I hope you're ready for that. Hope you've had a good breakfast. And as well as some science, I also want to try and give a little bit of perspective about how the whole family of research administrators have contributed to this field, to this discovery, and actually without y'all, it really would not have been possible. So let's start on the science. I'm going to talk about gravitational waves, and to talk about that and about how we do astronomy in this new way, we need to think a little bit about gravity. And actually, in nature, describing how everything we understand in the universe works, there are basically 4 forces that govern everything. And gravity is one of those. And the 4 you can see up on the board there. Now, 2 of those you're probably all pretty familiar with, and gravity is one of those, because gravity, of course, is what holds us here on the surface of the Earth. And you know that if you pick up an object, if you pick up some cutlery on the table, you let that go, it's going to fall. It will fall, and what's causing it to fall is gravity. So that you're pretty familiar with. The other one of these forces that you're probably familiar with is number 3 on the list there, the electromagnetic force. Because magnetism is something, again, you're pretty familiar with. If you have a fridge magnet, you hold it up to the front of the fridge, it will be pulled on and stick. And that's the electromagnetic force that's doing that. The other 2 forces, the so-called weak and the strong, are important really inside atoms. So every day we don't really experience those. But if we think about gravity for a second, again, you have a pretty good feel for how strong gravity is. You know if you jump up, you're going to come back down, and you know how that feels. So hold in your head the thought that that has a strength of 1 in some units. Let's compare everything to how strong gravity feels. If you think about the fridge magnet again, that fridge magnet, that force that's holding it onto the front of your refrigerator is many times stronger than gravity. And again, I've put on the slide there how many times it is stronger. It's in scientific notation. So kind of explain what that means, that 10 to the 37 there, well, if it was 10 times stronger, that would be a 10. If it was 100 times stronger, that would be 10 to the 2, 1,000, 10 to the 3, 10,000, 10 to the 4. So 10 to the 37 is almost unimaginably stronger than gravity. But gravity is probably one of the most important forces in our entire universe. It's by far the weakest, but it's hugely important. And why is that? Because it's always attractive. Okay? The fridge magnet can beat the whole pull of the Earth as long as you hold it close to the fridge. If you pull it a bit further away and let it go, gravity wins, because gravity is always positive. All mass attracts other mass. So on the scale of the universe, gravity wins. And in fact, it's responsible probably for the birth of stars out there in the universe and the death of stars. Clouds of dust far out there in space, every point in the dust cloud gets attracted to every other point until they collapse in. And in the middle, they actually start to fuse together the atoms and a star is born. And it's how that happens, how things behave under gravity was described many years ago by Newton in his law of gravitation. And Newton's law of gravitation is actually quite simple. It says if you've got two objects, some distance apart, they're attracted to one another. And how strongly they're pulled together depends on how massive they are and how far apart they are. So if one of those is the Earth, say, and the other object's a star, they're attracted to one another. They feel a pull, a gravitational pull. But if that star moves, the pull changes, and it changes instantly. So that would mean if we were here on Earth and a star changed its position on the far side of the universe, we would instantly know about it because we'd feel the pull. That feels wrong, that we could instantly know about anything on the far side of the universe, and it is wrong. It's not true. And it took Einstein to come along with what's called his special theory of relativity to say that no information can be carried faster than the speed of light. That's as fast as anything can go. And that includes any information about gravity. So if that star on the far side of the universe changes its position, it takes time for the change in the gravitational pull to get to us here on Earth. So there must be traveling signals that travel across the universe that carry information about gravity with them. And those are gravitational waves. Now, there's a whole bunch of complicated maths that describes what gravitational waves are, but we don't need that actually. We can have a picture of what gravitational waves are. So if we think about a star sitting in space, what relativity tells us is that star bends the space around it. It actually changes the position of points in space. What does that look like? Well, if you imagine a grid marking out points in space, a star will actually change distances around it in space. That's what Einstein tells us. We say matter curves space, and then that curved space is actually gravity. That curved space tells objects how to move. Okay, so now this is a lot for breakfast, but hold on to these thoughts. So hold on to that picture and think of space as our universe that we live in, as having if it was empty, a flat, empty space with a grid marked on so you could tell where everything was. Then we come along and we add a star to space. And what that star does is it stretches the space around it, like the picture on the board here. So if we've got a star and it's curving the space around it, if we came along and we put another object down, you can see what would happen. It would try and roll down that curve. So that curvature we can think of as gravity. It's what causes objects to be attracted to one another. It's the curvature in space. Now imagine the star does something violent, it explodes, it's going to change the curvature of space around it. That change in the curvature of space is, remember, the curvature is gravity, so the change in the curvature as it starts to ripple is telling us gravitational information about the star when it moved. So we sometimes use the phrase that gravitational waves are ripples in the curvature of space-time. Sounds terribly exotic, but that's the picture. Mass curves space. As that mass moves, it sends out ripples across the fabric of space. And it literally changes distances in space. So as we sit here in the room, actually we're being squished and stretched just a little bit all the time as gravitational signals come through from far out in the universe. Sounds like science fiction, but as we'll see, it's fact. So I said gravity was responsible for the birth of stars. It's also responsible for the death of stars. Say we have a star like our sun, and the sun's shining. Why is it doing that? Well, in the middle, atoms inside the sun are fusing together and giving out energy. That's happening all the time. That's burning hydrogen. However, gravity at the same time is trying to pull everything together, cause the star to collapse. These things balance out as long as there's fuel to burn. But when that fuel eventually runs out, as it does, gravity wins because gravity is relentless. The star will collapse. If it's a star that's slightly bit bigger than our sun, it will be catastrophic. The center of this star collapses in a very short period of time, blows off the outside. In what's called a supernova explosion, we would see a bright flash. And in the middle, very strange objects, strange kinds of stars are formed, called neutron stars. Very dense objects that we can't make here on Earth. Or if the star is big enough, nothing stops the gravitational collapse, and all the mass of the star collapses into a region of space where gravity is so strong that nothing can escape its pull. And that we call a black hole, a region of space with super strong gravity. If that happens, again, think of those ripples being sent out in space caused by the sudden stellar collapse. The picture you can see here, sort of on the right of the slide, is the aftermath of a stellar explosion. A star has collapsed, blown off its outside, leaving this beautiful shining, what we call a nebula, the Crab Nebula there. In the middle of that, we believe there's one of those neutron stars, and it's spinning many times a second. Hugely dense. If it's not a perfect sphere, if it's got a lump on its surface, and it's spinning round in space, think back to that rubber sheet. It's sending out ripples out across space, gravitational waves. And the size of those tell us about what size of lump there might be on the surface of that star. Now, these objects are objects that are made of material that we actually truly don't understand. They can only be made out in space. The pressures, the collapse, the densities are so strong we can't simulate that here on Earth. So space is our laboratory. And different kinds of material would make the neutron stars have a different kind of shape. So by detecting the gravitational signals, we can start to learn about how material behaves under conditions that we couldn't even make here on Earth. Say we have two stars, two dense neutron stars, or even two black holes. They get caught in one another's gravity and start to spiral round, losing energy as they do so, getting closer and closer together. They're causing dents in space, sending out gravitational signals. As they lose energy, they get closer and closer together, spiraling in, speeding up, until eventually they smash together and cause a ripple that goes right out across the universe. This is gravity that's super strong, again, pushing the boundaries of what we understand. So detecting the signals from that, again, lets us understand more about our universe. And lastly, black holes. If we have two black holes formed in stellar explosions, and they get caught in one another's gravity. They will also spiral in. And this little animation here shows them denting the space around them, and underneath you'll see a signal. And that is the stretching and squashing of distances in space that we would actually measure here on Earth as that signal traveled across the universe, arrived with us, and you can see it has a very characteristic shape. Let me just run that for you again. You can see when the stars are far out and we sit a long way away, we actually feel space being stretched and compressed slowly here on Earth. And then we'll skip ahead to where these black holes are closer together. The signal gets larger. The stretching gets bigger until the two black holes actually collide, merge into a new black hole, and that actually wobbles a bit. Again, all looks very gentle here, but this happens very quickly, and these are some of the most violent events that we can think of in our universe, really, again, causing huge distortions in space. But by the time the signal gets to us, it's pretty small. We have to work hard to detect it. And as Kathy mentioned at the beginning, that's exactly the kind of signal we detected for the very first time earlier this year with new kinds of observatories, gravitational wave observatories. And the plots up there on the board, if you look at the top one, that's the actual signal that the observatories detected. There are two observatories. I'll say a little bit more about those, one in Hanford in Washington State, one in Livingston in Louisiana. And they were actually feeling the universe vibrate, feeling space itself vibrate as the signals from colliding black holes far out in the universe came in. And you can see it looks very much like we predicted from black holes colliding. And encoded, built into that signal, is actually the properties of what produced it. We know it was two black holes. You can see that characteristic shaking of space itself as these black holes spiraled in, combined into one, formed a new black hole. And this is the first time anyone's ever seen the birth and merger of a black hole this way. It was indeed a historic discovery, verifies predictions made by Einstein 100 years ago, and it was announced again this year, 100th anniversary of the prediction of these waves, these gravitational signals, detected in September last year, which was the 100th anniversary of the theory of relativity, general relativity, being created. So it came at just the right time. And when we start to look at that signal and look at the information in it, it becomes even more incredible that we were just ready for it coming. You don't need to read the details. That's the abstract of the paper describing this discovery. But what it tells us is, from that signal, from that trace, we can tell, for instance, the sizes of those black holes. We know that one was about 36 times the mass of our sun. The other one was 29 times the mass of our sun. And we know how far away out in space that collision happened. It happened 1.3 billion light years away. Now, although it says years, light years is a distance. It's the distance that light travels in 1 year. Almost unimaginably far. So it happened, in fact, 1.3 billion years ago, and that signal was traveling to us across the universe ever since to arrive on 14th of September last year. We can tell, again, from that squiggle, from that signal, that the final black hole was 62 times the mass of our own sun. So that's equivalent to about 20 million times the mass of our Earth, but actually squashed into a region of space that's about the size of Iowa. Or, again, for our European visitors here tonight, that's about the size of Iceland. 227 miles across, but 20 million times the mass of the Earth squashed into that tiny space. We can tell it was spinning about 100 times a second. And that on the edge of that black hole, a point on its surface was spinning at nearly half the speed of light. amazingly fast, and it's all encoded in that little signal. And what's kind of amazing is that this collision, this far out in the universe, produced no light. We would not, we think, have been able to see this with any kind of conventional telescope. It required these gravitational wave detectors to be able to detect this event. And in fact, it wasn't the only one. That was the first one announced in February, detected in September last year. But there was a second black hole collision detected in what was December 26th in Europe, Christmas Day here in the US. Again, a nice Christmas present. And there was another signal, not quite as large as those ones, but possibly another event in October. So we're starting to actually be able to do astronomy, to survey the heavens and detect, again, these new kinds of signals. And it really is new. Again, it really is exploration. We are able now to study the universe in a way that we just couldn't before. So this plot gives you an idea, again, of the size of those black holes. Again, up the side is a number of times the mass of our own sun. And with telescopes that detect X-rays, again, people had an idea that there might be black holes out there between 10 and 20 times the mass of our sun. And what's plotted on the slide there is pretty much all the information we had from about 40 years of X-ray astronomy, using X-ray studies to study the cosmos. In 4 months of running of the gravitational wave detectors, we've already detected large black holes, more massive than have ever been seen before. Again, so it really is entering a whole new way to study our heavens. And in terms of catching the public imagination, in terms of engagement, again, when this was announced in February last year, it made headlines, not just in the US, but actually around the world. Again, it was front page news. It was top of the news hour in the UK, again, that day. And this is just a small selection of some of the newspaper front pages. The Washington Post, I think's in there, the New York Times, the Independent in the UK. There are newspapers there from Spain, from Germany. Some of them are in languages that I do not recognize. It really was global news, science, research on the front pages, and a good news story around the world. That was fantastic. So how do we do these detections? Well, let's think more closely about what we're doing, these gravitational waves are doing. They come in from far out in the universe. They come in, they travel through space, they come in, they hit the galaxy, they come down to the solar system, they hit us here on Earth, they come in through the room here, travel through the board, and that is what a gravitational signal coming from those signals far out in the universe would do to a patch of the board. It actually would stretch and squash distances on the board, literally would change the dimensions of the board, and that's what we're trying to measure. But it doesn't change it by very much. A typical gravitational wave would only stretch those points on the board by, again, scientific notation, 10 to the minus 22 meters. What does that mean, to give you some scale? Well, the width of a human hair is about 50 microns, 50 times 10 to the minus 6 meters. The size of an atom is about 10 to the minus 10 meters. So 10 to the minus 22 is many, 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 many times smaller than the size of an atom. So it's not changing by very much, and we need a very good device to measure that. And basically what we do is we use light as our measuring device. We take light, we actually split it into two. That light goes up, and it senses, measures, samples the position of points, mirrors that reflect the light back where it adds up again. We look and see what's happened. Well, how does that help us? Okay, remember what's happening. The points, in this case, these mirrors, you can think of it as that point there, the other mirror is this point here, are moving as a gravitational wave goes past. Think of the light as a wave. That light's traveling out, It's traveling out as a wave up this arm. So the wave goes out, bounces off, the wave comes back. Same thing happens along here, the wave goes out and comes back. So these waves of light go out. If when they come back, we've got a peak, you can think of it as like a water wave having a peak. If you've got two waves at a peak, they add up, you get a bigger peak. We'd see a bright spot if we looked here. If, on the other hand, a gravitational wave has come past, changed the length of the arms, it's moved this mirror, so it's moved that mirror out, moved this mirror in, then one of those waves might come back as a peak, the other one's traveled a different distance, comes back as a trough, they cancel out, and we get a dark spot. So we literally look at the brightness of the light to see if anything's changed by a gravitational wave going past. Now, as you might guess, in practice, the instrument that we've built is much more complicated than that, and it actually took years of development in the lab, actually decades, starting in the 1970s in labs around the world with people trying to make these instruments, again, a global effort, until in about 1989, we realized we need to make these detectors bigger to make these events, detections. There were proposals for big instruments that were created around the world, and of course here in the US, that was the LIGO project. And that was a joint proposal from Caltech and MIT to the National Science Foundation to build a gravitational wave observatory. And again, it's a decades-long challenge, and you can see I lifted these from the proposal, straight from the proposal that went into the NSF. And the scientists at the time knew it was going to be hard. There's nothing more difficult to take in hand, more perilous to conduct, or more uncertain in its success than to take the lead in the introduction of a new order of things. From, again, 1513 Machiavelli. So they knew they were proposing something hard, but the prize is big, a new observational window on the universe. And that proposal, again, it's nearly 400 pages, it was, and I think perhaps still is, the largest project that the National Science Foundation had ever funded. Again, it's a major proposal. And it created the LIGO observatories, and as I said, they're located one in Hanford in Washington State, one in Livingston in Louisiana, operated by Caltech and MIT, again, jointly responsible for their running. And so these are giant versions of that cartoon that I showed you. This is the Hanford Observatory. You can see the central station there, about the size of a supermarket, long 4-kilometer arms. The other instrument is in Louisiana. You can see completely different environment. It's actually in a swamp, again, about an hour from New Orleans. Huge installations, again, sitting there trying to listen, feel these vibrations coming in from far out in space. And the initial versions of these weren't quite sensitive enough, so there was another proposal, again, that went into the National Science Foundation to upgrade those. Again, another substantive proposal. And that, again, supports and sort of has been put into place both by what's called the LIGO laboratory, about 180 staff at Caltech and MIT and out at the observatory sites. But this really is a global endeavor. The science is done by a huge collaboration, about 1,000 scientists, about 80 institutions, and 14 countries. And to do the second stage, to make the instrument sensitive enough, required both intellectual and hardware contributions, financial and hardware contributions, internationally, again from colleagues in Germany and Australia, and again from a group from my group in the United Kingdom and colleagues there. Now, as you can imagine, with a project of this size, the administration challenges are significant, again, with financial challenges, institutional reporting, again, oversight requirements from different funding agencies and these international partners, all having to work together with, again, colleagues in the US for requirements here. And again, just one example, in my own institution, we had a substantive award to supply hardware. We needed to buy components from Germany. they were going to end up in the US permanently here. There are strict European laws. It was a substantive award, substantive procurement challenge, and so we had to work very closely with experts in Glasgow on the tax implications, on the exporting of that, which had to be bought in Germany and shipped to the US. So large, again, underlying challenges. Especially when you consider, again, that was just one aspect, but making this all work requires the input, again, of scientists right across the globe, all working together to make this happen. So once you start to think about the details, actually, the science that I talked about starts to look easy in terms of actually making the project work. LIGO itself, again, I on giving this talk, talked to the LIGO director. Again, LIGO itself has a business administration group who take care of the finances, the contracts, the subcontracts. Again, Caltech and MIT subcontracted other US institutions to do part of the work, make sure the bills get paid, HR, and of course the substantial reporting requirements on a project of this size back to the NSF for taxpayers' money. As I'll say a little bit about, there will actually be a new instrument, a new LIGO detector, which will be sited in India. Again, that brings its own, again, challenges in terms of exporting equipment to India to be sited there. So there's export compliance, licensing expertise, again, supplied by Caltech, legal advice. The Advanced LIGO project itself had a dedicated office, again, to deal with the demands of, again, that second stage advanced LIGO proposal, again, which was about just over $200 million. And I think what's remarkable, actually, in terms of not just in terms of the project, is that it didn't just do fantastic science, it did it on time and on budget, which for a project of this size, I think, is actually quite remarkable. It was phenomenally well managed. So it is exciting science, and in the project, we want to make sure that we communicate the excitement of that. It's science that rewrites the textbooks. So within the collaboration, again, we have people who work exactly on that, on both the outreach and actually the education part. So this is an educator's guide, actually, for students, again, for teachers to try and teach the concepts associated with this detection, get those embedded in classrooms, because it's incredibly important that we have a new generation of people excited about science who are coming in, not just to do the kind of fundamental research that I've talked about here, but actually its wider, understand its wider impact. Because what I've talked about is the fundamental science, and I skipped over the details of how those observatories were technically built. Required considerable technological advances, which themselves have brought an impact. It's a rich source of spin-offs. Again, where support in translating those out into improving the economy, into helping society is incredibly important, and these are just a few of the examples of what we're doing now. So spin-offs from the technology are actually going into the area of healthcare. A couple of different areas there. We work with a company that actually makes machines, a company called Optos, to do retinal scans of the back of the eye and look for defects in the retina that might indicate medical problems. Those machines, due to the way they work, can have artifacts due to their scanning nature. And you want to be able to distinguish those from real problems, and we actually take some of the techniques that we use to analyze the data from the gravitational wave detectors and apply those to improving the quality control of the machines that actually do the retinal scanning. Some of the other techniques are actually, we're working with biologists. Stem cells, fundamental cells in the body that can change into all kinds of cells. We're using vibration and interferometry techniques to control how those stem cells change and control them to change into bone cells. And so there's work there that's being done, again, that's targeted at helping people recover from orthopedic surgery, or people with soldiers with blast injuries coming back from the battlefield. And there'll be in-person trials, I think, of some of that technology in the next 1 to 2 years. There's a whole variety of these. Weathering of sandstone, we're working with agencies to monitor how historic buildings are actually decaying under climate effects. So it's a rich source of technological spin-offs, and again, that requires business development managers to help us understand what the markets are for the kinds of things that we can do spinning off from this technology. So what comes next? Well, I talked about the LIGO instruments, mentioned India, because actually there's a network of these observatories that either have been built or are being built around the globe. So LIGO turned on last year. The Virgo project, a project in Europe, should come online early next year. There's a detector being built in Japan, and hopefully, again, we have a smaller detector in Germany, and there'll be a new LIGO instrument built in India. And so you might see, why do we need this? Again, we've seen signals with just 2 instruments. Well, we need to be able to tell where in the universe they came from. And to do that, what we actually do is we check when they arrived at the different detectors. The first signal we detected actually arrived first in the Livingston Observatory, and then a little bit later, a few milliseconds later, it arrived in the Hanford Observatory. So we can tell some information about where it comes from, but not very well. We want to know where it came from so that we can talk to our colleagues in the astronomy community who have telescopes, because whilst the black holes may not have produced colliding, may not have produced any light, some of the other things will, like those exploding stars, the supernova, and we want to work together on that. So we need a network of detectors, widely spaced, timing when the signals arrived at each one, to give that information to people who can point their telescopes and look and work together on that. So we need the network for that. And I talked about the spin-offs, but of course, really what we've done is we have developed a whole new way to study the universe out there, to learn things about it that we couldn't learn before, to help us answer very fundamental questions about what's out there, where did it all come from, and where's the universe going? I won't talk in detail, but there's a whole list of questions there. And we need to do that. Again, fundamental curiosity, since man first stood and looked up at the sky and wondered where did it all come from. Again, we know currently that when we look up and we look out there, of the stuff that we understand, that we see, it's only a small fraction of the stuff that's out there in the universe. It's just a few percent. In fact, we can tell from the way that galaxies and stars are moving that there is other stuff out in the universe that doesn't emit light, but it has gravity. We see it has gravitational effects. We don't know what it is. We call it dark matter. We have no idea what it is. We also know that the galaxies are moving apart as we look out. They're not just moving apart, they're rushing away from one another faster and faster. We don't understand what's causing that. We see it's something called dark energy. No one knows what dark energy is. We simply don't understand. We need new physics, new ideas, new science. And so understanding our universe through its gravitational signals is particularly interesting. Every time someone has turned on a new telescope, these are all pictures of the sky taken with telescopes of different kinds. And you can see it looks completely different depending what kind of telescope you use to look, whether you look in the optical, whether you look at X-rays, whether you look at ultraviolet signals or radio signals, completely different. Already with gravitational wave detectors, with these colliding black holes, bigger than we expected, it was a surprise. We've seen things that we didn't necessarily expect. So one of the most exciting things is what's coming next. So just to finish, again, when I explained to my colleagues in LIGO I was going to give this talk, I got an email from Joe Giami, who's head of the LIGO Livingston Observatory, and verbatim, this is what he sent me. Many or most scientists whose scholarship benefits from the work done by sponsored research personnel are blissfully unaware of how to balance institutional legal, procedural, IT, personnel, logistics, or how to deal with other sources of constraint and risk. Scientists simply often don't know. For projects like this one, again, which are multi-institution, he points out every multi-institution collaboration requires a leap of administrative faith and perceptive interpretations, sometimes, of rules and requirements to conclude that it's all legal and it will all work. But without that, there would be little or no collaboration and science would suffer. I would go further than that, and I'd say that science, in fact, certainly the things that I've talked about today, just would not happen. So I would like not only to thank the organisers for inviting me to come and speak today, but I would like to thank you for the hard work that you do to make us able to do what we do. Thank you very much.
We have a few questions that have been sent in for Sheila. Please remember that on your table, you can submit questions by texting or tweeting to those instructions. So Sheila, our first question is, what's the significance of black holes? Do they give us hope for other life or possibilities of life?
I'm not sure about possibilities of life, but black holes are an incredibly interesting, strange object. I mean, every one of those, again, pushes us to the edge of what we understand about our universe. They create a region of space from which no information comes from inside a certain distance. Things disappear into a black hole. Again, gravity is super strong. They represent somewhere a region of space inside which we don't know how to apply our current laws of physics. So probing black holes, probing what they do to space, pushes our understanding of the laws of physics right to its limit. And that's always where you make new discoveries, when you're pushing right to the edge of what you understand. So they are, from that point of view, incredibly interesting things to study, especially since, back at the beginning, I said there was those 4 forces that governed pretty much what we understand. 3 of those we can combine together. We can write down theories of how physics works that combines the 3 apart from gravity. We cannot make all the theories fit together. Black holes have the strongest region of gravity that we understand. So pushing on those, again, we hope may lead to breakthroughs, again, that have wider implications across our understanding of physics.
Thank you. And one other question. We often say in our profession that no one grows up thinking, I'm going to be a research administrator. Did you grow up thinking that you were going to study gravitational waves?
So I didn't know that I was going to study gravitational waves, but I did grow up believing I wanted to be a scientist, actually from when I was quite young. Actually, I think the first thing I wanted to be was a journalist. I found investigative journalism very interesting. I wanted to be a journalist. But quite quickly, again, when I was quite small, again, I'd be about 9 or 10 years old, I became fascinated with science, with astronomy, with cosmology. Again, the questions I think that many people fundamentally ask. You know, if you started out traveling through space, how far does it go? How far can you go? Where's the edge? Where did it come? Where did all the stars come from? You know, those big questions. And when I was young, found that so interesting that I really couldn't think of a more exciting way to spend my time was trying to study those things. Didn't know gravitational waves was where that was going to take me, but I did actually want to be a scientist, yes.
Thank you very much. thank you, everyone who sent your questions in.
It's been an absolutely fascinating talk. I personally learned a lot. I'd just like to thank Professor Rohn for coming all the way here to our conference and for starting it, setting us off on such a great footing. And so, on behalf of colleagues at SRA, we've just got this small thank you.
Oh, thank you very much. That's
so you can remember us all.
Thank you very much.
Thank you so much.
Thank you.
Thank you so much. So it just remains for me now to say to you that on behalf of the conference co-chairs, I hope you all have a productive meeting, and let's make San Antonio a meeting to remember.
So, okay. We can go that way.
Fix the things as well. Jim Hafting.
One evening when the sun went down and the jungle fires were burning, down the track came a kiddo hiking, said, boys, I'm not a turning. I'm headed for a land that's far away beside the crystal fountain. Come with me and we'll go see the Big Rock Candy Mountains. In the Big Rock Candy Mountains.